another meaningful property associated with the systems is the time invariance. Okay. Now, what does this transformation means conceptually? Is that a system is time invariant if the behavior and the characteristics of the system are fixed over the time. Okay. So it means that the system is not changing its characteristics over the time. So, for example, if you have a certain, say, a continuous time system (CT), and you apply an input, call it x of t, a time varying input x of t, which is a certain waveform, then the system interacts with this xt and produces a certain output, call it y of t. Now, if the system is time invariant, then uh, then uh, then if you apply an input, the same input, which is delayed by some finite interval, call it capital T, then as a result, as a consequence of that, the output that we had previously, y of t, this y of t, will also be delayed by the same amount of time. Okay, so you can say that this is a waveform preserving transformation. What it means is that, okay, now if you have this xt, any arbitrary input, time varying input, you have an output corresponding output y of t. So let's say y of t has a variation with time. This is my independent variable time, and it might start at 0. Okay, a certain waveform like this, whatever it is. This is my y of t. Okay, so this is a rough sketch of y of t. So what happens when you apply the same input delayed by a certain finite interval capital T? This produces the same output. The output is in the waveform should stay preserved if the system is to be classified as time invariant. That means after a certain interval capital T, certain finite interval capital T, you will have the same shape of the waveform. So if we can reproduce this exactly, yeah. So you see this output is represented by y of t minus capital T. That is, you see, once the input is delayed by capital T, which is being applied at capital T, you can't have an output before capital T. So it's the waveform simply shifts itself. Okay, the waveform is preserved. So it's like applying an input after a certain time period, let's say after 1 hour. The output, the same output y of t appears after 1 hour. Okay, or a finite duration of time, whatever it is, 1 day or 10 days or a month. The same waveform should appear, okay, with the same time delay. Then you classify the system as time invariant Ti or time invariant Ti. If not, then this is the time varying system. So conceptually, let's try to understand. Let's take a few examples. I mean, intuitively. So, for example, let's consider an RC circuit. Okay. For example, RC physical circuit is time invariant if the resistance and capacitance values of RC are constant over time. What does it mean? It means that if you excite the same circuit with a certain input, you're going to get the same results. Okay, so we would expect the same results from an experiment with this circuit today as we would if we ran the identical experiment tomorrow. So it doesn't matter, given as long as the lumped element values of the circuit are not fluctuating with time, they stay the same. The experiment that you are going to run, you're going to excite the circuit by a certain signal, let's say from a function generator, and measure it on an oscilloscope. Given the lumped elements, the configuration stays the same, the circuit stays the same, RC doesn't change, there are no room temperature pressure conditions changing, nothing that affects the values of R and C. The output is going to stay the same. The experimental output, we would expect the experimental output to stay the same. Whether you run the experiment today or you run it tomorrow, you will expect the same consequence, the same result. This implies time invariant system. Okay, Ti. So on the other hand, if the values of RC are changed or they fluctuate with time, then we would expect the results of our experiment to depend on time at which we run it. Okay, So at time, whatever the value of that RC is, the experimental output is dependent on that value at that particular time. So in that case, the system becomes time varying or TV. Okay. So then that is not time invariant system. Similarly, as another example, suppose if you have a certain friction coefficient B of an automobile having a mass m, okay, then these things are constant, these parameters are constant, then we would expect the vehicle to respond identically of when we drive it. So if the drive condition is the same, I mean, if the loading is the same, the mass is not changing, then you will experience the same driving condition, whether you drive it today or later, a week later, whenever. So, but on the other hand, if, for example, you change the mass of the vehicle by loading the automobile trunk with heavy suitcases, then one day, thus you increase the mass. So one parameter changes, then we would expect the car to behave differently, okay, than at the other times when it's not heavily loaded. So you see, if you change one parameter of the system, if certain parameter in the system changes, the output changes. Okay, then the thing is, if you're, let's say, if you have, if I put it like this, if an input is x1t and the output is y1t, okay, so at another instant you apply an input x2t and you have an output, y2t, okay, you have an output y2t. Now the question is your y2t, although the input x2t has a relationship with x1t, that x2t is equal to, I can write this as such, x2t is the same as x1 of t minus capital T. Although my x2t is the delayed version of my original input x1, the question for the system that stands, whether you before we qualify the system as time invariant, is that whether y2t is equal to whether, so there is a question mark on this equality, whether this is equal to y1 of small t minus capital T, whether the waveform is preserved, or you might say that the output with time is preserved or it is delayed by the same amount of time. If this equality holds, then yes, go ahead and you qualify the system as time invariant. Okay, if this is not the case, that means some parameters in the system have changed and the output has not been preserved. Therefore, the system becomes time varying. So that's the idea behind time invariance. So specifically, in terms of in language of signal systems, we say that the system is time invariant if the time shift to the input signal results in an identical time shift in the output signal. Okay, so that's what we have been discussing, illustrating over in this example over here, right? So if you have the same delay in the input signal, the output should also be delayed by the same amount. Okay, it should not be twice t, 3t, or y2t, which has a half the amplitude of y1t. No, it has to be the same waveform, just the same amount of delay that the input has suffered or taken. Okay, so if that's not the case, then the system is time varying. So mathematically, if yfn is the output of the discrete time system, then the time invariant system, when xn is the input, yn minus n naught is the output. That is when xn minus x naught is applied. So in a continuous time system, yt, the output corresponding to the input xt, is a time invariant system. If you have yt minus t naught to the output as an output, when xt minus t naught is the input. Okay, so whether it is discrete time or continuous time, the input is delayed by a certain interval t naught. If it is a continuous time system, the output should also be delayed by the same amount, yt minus t naught. So in that case, the system, you can say this is time invariant. Otherwise, it's time varying. Okay. Let's take a few examples. So this is example 114, and it considers a continuous time system which is defined by yt equal to sine of xt. So the sine function in its argument is taking a time varying signal x of t. So to check whether the system is time invariant, we follow the same procedure of checking the system. That is, we must determine whether the time invariance property holds for any input that is delayed by or shifted by t naught. Thus, let x1t, then let x1t be arbitrary input. To check the system if it is time variant, we introduce a certain input x1t. So this is an arbitrary input applied to the system. Whatever the output comes in response to x1, we call this y1t. Okay. So again, you have applied to the system an input. This is the system x1. So again, the output is y1 of t. Okay. So we have the output y1 of t. But y1t, since y of t and x of t is a certain relationship being described by uh, the system is just taking the sinusoid of the input. So y1t is basically sine of x1t. Okay. Now this is the corresponding output. So then consider a second input obtained by shifting x1t in time. That is, you now introduce another input x2t, which is just a delayed version of x1t as we've talked before. So x2t is my, in fact, this is my x1t waveform, just shifted in time with a certain delay, call it t naught in this case over here. Now, the question that remains is that in response to x2t, the system produces another output, y2t. Now, does y2t and y1t, are these related? So let me put the same question mark over this equality. Are these related by the relationship that y2t is equal to y1 of t minus t naught? Well, we can look at this analytically by considering the equation, the input-output relationship. So you see that y2t uh, is the output of the system in response to x2t, and x2t is my x1 t minus t naught, which comes over here. And this, if you try to relate this with y of t, you can write this as y1 of, okay, like here. So y1 was in response to x1, so you can write this as y1 of t minus t naught. I mean, you can see this. This is quite evident. So comparing it with the output y1, we see that y1 t minus t naught is to sine x1 t minus t naught, which is nothing but x y2 of t. So yes, the equality, the equality that we questioned before does hold. Yes, so that's okay. That means you can. This simply means that y2t is the output has been delayed by the same interval that the input was delayed. So input was delayed by t naught, and that constituted another input. So the second output was the first output, which is delayed by the same amount, t naught. This implies time invariance. Okay, so this is the procedure of checking the system for time invariance. Okay. Okay, now this is another example. Let's try to illustrate the same effect of checking time invariance. This is the second example. So now we consider a discrete time system. Y of n is equal to n x of n. This is a time varying system. This is a fact that can be verified using the same formal procedure as we've done in the preceding example. Well, this, you see, what you do is, okay, my system, I call this the output y of 1 of n to an input, arbitrary input, call it x1 of n. X is my input. Okay, so you mind that x of n is the input. N is just a multiplying factor, so you don't need to bother about that. So, but it does play a vital part in determining if the system is time varying or it is time invariant. So this is my output in response to x1. Now I introduce another input x2 of n, and this x2 of n by the same procedure that we have discussed in the previous example is the delayed version of the original input. Okay, so this is x minus n naught. So x1, x2 are my arbitrary inputs. Only the thing is, what we are assuming is that x2 has a relationship with x1, that is x2 is the shifted version or delayed version of x1. Okay, nothing more to that. Then in response to x2, we are expecting an input y2 of n, which can be written as n x2 of n and x2 of n. And you see that if I substitute this for x2 of n, I can write this expression again as n of x1 n minus n naught. Okay, so what does it mean? It means that y2 of n, okay, so y2 of n is not equal to y1 of n minus n naught. If you can see this a little bit more closer, you see y1 of n was nx1 of n. So my y1 of n minus n naught would be equal to n minus n naught. You see there is an n over here as a multiplying factor, so you have to replace n by n minus n naught. Wherever you find n, you replace this by n minus n naught. Then x1 of n minus n naught. So now you see y1 of n minus n naught, this expression is not equal to y2 of n. So we can't compare these two expressions. So the equality doesn't hold. This means the system is time varying. So this is the idea. I mean, if the input is being delayed by the same amount, the output is not delayed by the same amount, which has happened in this case. The system is time varying. So intuitively, I mean, this is one way. So you see, whenever you are suspecting, whenever the system is being suspected of being time varying, an approach to showing this is to often very useful approach is to seek a counterexample. That is to use your intuition to find an input signal for which the condition of time invariance is violated. Well, we didn't find any specific example, particular example. I mean, the thing is, you can give 100 examples to prove anything, but the idea is that if you give a counter example that violates the assumption, underlying assumption, then that violating example is a sufficient and enough proof to show that the system is not qualified for a certain property. Okay, so what we did over here was to take the general arbitrary sequence, and this proof is in general. Okay, this is a general proof, not for a particular signal. Okay, so this proof is also good enough, or I would say sufficient, to say that sufficient proof to show that the system is time varying. But if you have to take a counter example, if you can find an input signal that does make the system violates the assumption of time invariance, well, that's another way. So what is the idea is, let's over here you consider input signal x1 of n as delta. This is not 8, this is delta. Okay, this is delta. Let me correct this. This is delta again over here. And so delta, let's replace this by delta first. So now my input is the delta function. Okay, and this is a discrete impulse, which is a unit sample that exists at n equal to 0, otherwise it's 0. Okay, I mean, you know that this delta of n only exists at n equal to 0, otherwise it's 0. So at n equal to 0, then you have the unit sample, otherwise it's 0 elsewhere. So like this. Dot, dot, dot. This is my delta. Okay, now so I have the same system. The system is my discrete time system, which is defined by the relationship y of n equal to n of x of n. Okay, now to this system we apply an input. X1 of n, which is equal to delta of n. All right. So what is my output? I mean, you can very easily say that this output is y1 of n. y1 of n equals to n delta of n. Now you understand that this delta of n is non-zero at n equal to 0, which means that the output is 0. Okay, because this delta function is 0 everywhere where n is not equal to 0, but for n equal to 0, this multiplying factor becomes 0, so the output is 0. Now what happens when I have another input x2 of n, and that is delayed by a unit sample, which is equal to delta of n minus 1. Now, do I have an output which is y1 of n minus 1. So look, y2 of n over here becomes equal to n. We are not changing n. The n stays the same. So y2 of n becomes n of delta n minus 1. Okay, and this impulse only exists at n equal to 1, which means the output is 1. So you can see that y2 is y2 of n, or I can drop n over here. Anyways, y2 of n is not equal to y1 of n. That means that my system is time variant. This implies the system is time variant TV. Okay. You see, we have taken a counter. So this proof is also good enough. This is a counter example that you can take hundred of examples, but one example, that one signal you can think of that violates the condition of time invariance is good enough. I mean, this proof was also enough. But anyways, this just to show the approach, you can take a particular example, take a signal, and then shift it and see if the output is shifted by the same amount. If it is not shifted by the same amount, then the system is time varying, which happens in this case, which has happened in this case. Okay, it's time varying. It's time varying. Okay, now. Let's consider another system. This is a continuous time system. Yt is x2t. Now you can see that this is a time compressor. Okay, the system is compressing your input by a factor of 2. So this represents a time scaling. That is y of t is time compressed by a factor of 2 version of xt. Okay, so yt is a time compressed factor of 2 version of xt. For example, over here you have x1t. If you apply a certain input x1t, which is the duration is from -2 to +2, otherwise it is 0. Okay, elsewhere it is 0. What happens is that this is compressed in time, -1 to +1, and you can understand this why. Okay, so because if I put, okay, so what is my y of, so y1 is my y1t is my x1 of 2t, right? X1 of 2t. So you see y1 of 2 is my x1 of 4, and if I, without loss of generality, write it plus minus 2, then x1 of plus minus becomes plus minus 4, which is 0. So I don't have anything at 2, right? So I don't have anything at -2, I don't have anything at +2, and even beyond that, I don't need to consider. I don't need to consider plus minus 3, plus minus 4, or whatever. Okay, even the decimals or fractions. So the output occurs y1 at, in fact, this occurs at plus minus 1. So this makes it equal to x1 of plus minus 2. Plus minus 2. Therefore, this is still 0. But if I put a y of 0, then y1 of 0 is x1 of 0, which is 1. So at 0 it takes 1. Okay. So you can say that, you can see this over y1 of 0 is my x of 0, x1 of 0. So it takes the value of unit at time t equal to 0. At -1 and +1, it is 0, but then the signal exists between -1 and +1. I mean, you can put any values, even 0.5. For example, over here, this is minus half. Sorry, plus half. Over here, it's minus half. So at plus minus half, x1t is 1. Okay, so y of plus minus y1 of plus minus half is my x. This can be written as x1 of, if you put 2t, 2 of plus minus 1/2. So I'm just showing that this is indeed a time compressor by a factor of 2. That's all. This is the factor that is compressing the time. So this is x1 of plus minus 1. Now you know that at plus minus 1, which is somewhere over here in x1, the signal is taking the amplitude of unit. So that means at t equal to plus minus half, if it is less than 1 on either side, The signal is unity. Okay, so that is the case. That's how it compresses the time. Okay, but let's check the system for time invariance. If it is time invariant, you delay this input by an arbitrary delay. Over here, we have a delay of 2 seconds, for example. So this the signal shifts to the right. Okay, and this 2 becomes 4, minus 2 becomes 0. Okay, now what happens when this system operates on x2? It produces an output y2. That is again a time compression. For example, the same time compression that has occurred over here, the same time compression occurs in parts from part C to part D. That is from 0 to 4, the signal is compressed from 0 to 2. Now, if you consider the original output, okay, because you see x2t is related to x1t, which is the delayed version of your original input signal, x1t. Now the question is y1t is y1t equal to is y2t equal to y1 of t minus 2? Well, y1 of t minus 2 is something like this. So this, its center, which is 0, is shifted to 2. Okay, and this is not equal to y2 of t, which means that the output y2, which is in response to x2, which is the time delayed version of original x1, the output y2 is not the same delayed version of y1t. Therefore, the system is not time invariant. The system is time varying. So the time scaling system is time varying. So you can read the description over here. The inputs x1t to the system in example 1.16 is shown in these figures. And well, this is figure A, which is showing the original x1t. And the output y1t corresponds to the x1t, which is the time compression by a factor of 2. Then in part C, you have the shifted input x2t, and in part D, you have an output y2t. So basically, to the given input x1 and x2, you are having time compressions, right? But when x2 has a relationship with x1, that is, it is a delayed version of x1, the output is not the delayed version of the original output. So the shifted signal x y1t minus 2, note that y2t is not equal to y1t minus 2, showing that the system is not time invariant. Therefore, you qualify the system as time varying. Okay, so that's the idea. That's how you have to quantify the system as time varying or time invariant. If the output is delayed by the same amount, and if the waveform is preserved in time, well, yes, waveform preservance is one, but you have to see if it is delayed by the same amount of time. That's important. So if it is delayed by the same amount of time, well, yes, then the system is time invariant.